Okay, good afternoon. Just two more slides remaining in diodes, and then we'll pick up again in BJT. So do you have any questions about the diode wave shaping circuits? Let's bring up the notebook. Okay, so diode wave shaping circuits, the two ones that we saw were the diode clippers and the diode clamper. Does everybody understand how it clips and how it clamps? Any questions from anyone before we move on? I know we're especially rushed for the clamper, so. Want a recap? No? Okay. Let's see. Regulator. One point before I move on is the same as for the clipper. This is a negative clamper. If we want a positive, then we simply switch diode direction. Okay, and there are other multiple combinations. We can introduce DC power supplies in there. We can configure two or more diodes in the same line, and we can have a variety of clipper and clamper circuits. Yes. No. So a question being asked is what happens if the input is not a sine wave? The answer is nothing. We simply obtain the exact waveform at the output that we send in at the input. The only difference would be on the level of the DC component of that voltage. So that's a good question, actually. So we can see here, input is a sine wave, output's a sine wave. The only difference is this DC component right here. This is a DC component that is added on to our AC signal, AC waveform. So all clamper circuits work with the same philosophy. And the reason for that is once the capacitor reaches full charge, it behaves like an open circuit for DC. So it acts like a battery, right? Depending on the value of the capacitance, it's not going to discharge much through the diode. And so this capacitor behaves like a battery. Or basically like a DC voltage source. And that capacitor voltage is available at the output. That's why this circuit works. Okay. So we saw one application of the diode previously as the diode clipper, right? Basically clips. What is the downside of this clipping circuit? The downside is if we want a particular voltage level to be clipped from our output, then we need to have an extra DC source in there. Okay, that's the downside. So if we have a single diode without any source, we can only have 0.6 volts that is required for the diode to conduct. We can increase it to 1.2 by keeping two diodes in series. If you want 1.8, 2.4, we can only get in multiples of the diode voltage drop. If you want any other number, we need to have a DC voltage source. So that's one of the downsides. Okay. So a similar clipping circuit can be created with a different kind of diode. Zener diode. The Zener diode holds the output voltage constant. So if you use a Zener diode, no matter what the input is, the output is going to remain constant at the Zener level in the reverse bias. So clipping circuits can also be made with Zener diodes. Okay. So the advantage and disadvantage using a Zener diode is the same as the regular diode, is that the level of the voltage that would be clipped would be exactly the same as the Zener diode rating. So if you connect a Zener diode in reverse bias, let's say it's a 5-volt Zener diode, then it would clip up to 5 volts or anything above 5 volts, sorry, right? Output will stay constant at 5 volts. So that's a benefit and a downside. The downside is that if we wish to change, there are some applications that may require it. So let's just say if there were some applications that required a different kind of voltage, you would not be able to easily do so. If you had a DC voltage, you can easily vary the DC voltage and do that. So depending on your application, we could use a regular diode or a Zener diode. One of the most common applications for this could be in a surge protection unit. If you have a 120-volt Zener diode and you connect it across your power line or power supply, if you have any kind of like lightning strikes or fluctuations in your voltage coming in, it will not, the Zener diode will conduct and it will not permit the output AC voltage to go above that 120 volts. Right? That's just a thought. Obviously, well-made surge protectors have a much larger and complicated circuitry. Okay, so that was clipper and clamper circuits, and the last one is photodiodes. Photodiodes, as the name suggests, operate on the principle of photons. All semiconductor devices are affected by light energy, okay? Whenever photons are incident on a p-n junction, several of those photons could transfer their energy into the electrons, and the electrons would acquire enough energy to break free of their bonds and become free to conduct. Okay, and that is the operation of a photodiode, basic principle of operation. So you have photons transferring their energy to electrons. Okay, and once electrons acquire sufficient energy, they are now free and mobile charge carriers, and so they are able to conduct. In general, when we speak of photodiodes, we are speaking of diodes that are going to receive the light. Okay. Technically, though, any diodes that are operating with the principle of photons are referred to as photodiodes. And that would encompass everything from solar cells to light emitting diodes. Okay, solar cells to light emitting diodes. That would be the technical definition, but in general, generally speaking, photodiodes is, when someone uses the term photodiodes, they're simply referring to the fact that the light is an input to that diode. Okay, the light is an input to that diode, which is the basic fundamental operating principle of a solar cell. Okay, makes sense? And then there are light emitting diodes. So if you have a p-n junction, we have electrons and holes crossing the p-n junction, the depletion barrier. Did anyone have a question? Online? Okay. So if the electrons, excuse me, the electrons and holes crossing over the junction, depending on the kind of material we have, excuse me. Let's say a material made out of compound semiconductor gallium arsenide. When recombination takes place in any semiconductor device, meaning an electron moves into an empty open spot, so an electron and hole recombine. When they recombine, they're going to release their energy. Most semiconductor materials will release the energy in the form of heat, thermal energy. Hence, semiconductor devices get hot. Gallium arsenide, compound semiconductors, most of the energy is released as light. So when recombination occurs, electron-hole pairs recombine, then the energy that is released is in the form of photons. And hence we obtain light-emitting diodes. So it's the opposite. Solar cells and photodiodes, light is the input. For LEDs, light is the output. Okay. And the typical elements or materials that do this is gallium arsenide, gallium phosphide, any compound with gallium. Depending on the doping profile, you can tune the colors of the, so you can tune the wavelength of the emitted light, and hence we can tune the colors of the light. Okay. So nowadays, of course, it's become LEDs are ubiquitous. I think even in this classroom. No, these are still old fluorescent tube lights. But many of the classrooms, they've started replacing them with LED lights. Okay. So the university is going through room by room. All right, so that's LEDs. And that I would say is the end of our syllabus. But if you wish to do further learning, there are several other slides in there. There is one thing I will do, but when I come to this slide, when we actually get to logic gates, okay, logic gates. You can implement logic gates using transistors, but you can also do so using diodes. And so I will come to this afterwards. And then, as I said, there's some additional material in there. So if students wish to learn and go outside of the course material, you can do so. All right, let's turn our attention to BJTs. BJTs stand for bipolar junction transistor. Quick recap. 3 semiconductor materials connected in a sandwich form. You have a PNP and an NPN material. NPN transistors and PNP transistors. The 3 terminals are referred to as the collector, base, and emitter. Emitter is the most heavily doped material. Base is very lightly doped and is also very, very thin and small. Collector has even lighter doping than the base. So going from the lowest, collector has the lowest doping, then base has slightly higher, and then emitter is the most heavily doped of all 3. And so the way the device works is that the emitter would emit the charge carriers. In an NPN transistor, those charge carriers are electrons. In a PNP transistor, those charge carriers are holes. So the charge carriers will cross over into the base junction. They will combine, electrons will combine with holes. In a PNP transistor, holes will combine with electrons. But because the base region is very thin and very lightly doped, only a certain number of charge carriers are recombined. Most of them are free to hang out in the base region. But when we reverse bias or apply a opposite polarity to the collector terminal, which is at the far end, they acquire sufficient energy to cross over the base junction and they move into the collector. Hence the names emitter and collector. Emitters are the ones where the charge carriers originate, and the collector region is where they are collected or absorbed. And then they move out of the terminal and current flows through that device. Okay, so it's a 3-terminal device. And again, comes in 2 flavors, NPN and PNP. So in the lab and in the class, we studied a little bit about the application of a transistor as an amplifier, right? So let's look at a few more fundamental equations and fundamentals related to BJTs. Okay. The terminals are collector, base, and emitter. So the terminal voltages and currents associated with these 3 terminals are IE, IC, and IB. IE is the emitter current, IC is the collector current, IB is the base current. In general, the 2 equations that govern the voltages and the currents are noted right here. IC plus IB combine to give us IE. okay? Because all of the charge carriers are originating from the emitter, right? They're originating from the emitter. So emitter is the largest current in a transistor. So if you apply KCL, if we consider this as a single node and we apply KCL, we obtain the equation IA is IC plus IB. And then in terms of voltages, you have VCE, meaning the voltage measured at the collector with reference to the emitter, so VCE. And that can be split into two parts, meaning voltage between the base and the collector, and the base and the emitter. So if you apply KVL, we obtain VCE is equal to VCB plus VBE. Okay, these are the two fundamental equations for the voltages and the currents. Hey, any questions? So because of the construction of the transistor, the base region is very small. It does not have as many charge carriers. So by design, the base current is very, very small, typically on the orders of like microamps. Okay, compared to milliamps for the collector and emitter current, the base current is typically in microamps. So if you take this equation, IE is equal to IC plus IB, IB is typically in microamps, so about 1,000 times less than IC and IE. And since IB is so small, we can write IE is approximately equal to IC. Okay, IE is approximately equal to IC. And it depends on our use case scenario. We can apply different models. We can apply different analysis techniques. If you're trying to get an approximate answer just to see if a system works or not, oftentimes we simply take IE is equal to IC. And that works just as well for many analysis problems. Okay. Again, IB is very small. So many times we can simply approximate IE is equal to IC. So from there, come to the most important transistor parameter, is known as the beta. There are two of them, alpha and beta. Beta is IC or IB, also known as the current gain of a BJT. Okay, that's the most important parameter. It is also sometimes on the spec sheets, you will find it as HFE. HFE. That's from two-port parameters. I don't know, did you all do two-port parameters in 215? Maybe not. Okay. All right. Let's not get into that. It's a hybrid parameter. Essentially, we'll just take it. Essentially, it's the same thing as the forward current gain, forward active. Okay, so HFE would be something that you'd find on the data sheet, the spec sheet from a manufacturer. That would be the same as the beta current gain. So IC over IB. And then you have alpha, which is IC over IE. Again, IC and IE are very close in values. So if you're taking theoretical modeling and we'd say IB is very small, it's negligible, it's 0, then we could say IC over IE is equal to 1. Okay. For all intents and purposes, almost equal to 1. For most transistors, alpha is always like 0.99. Okay. Again, because IB is so small, the ratio of IC to IE is typically around 0.99. Okay, 0.99. Now, the reason beta is known as the current gain is because IB is the input and IC is the output. Okay. So if you all remember or recall, I used the example And I said, you have collector and emitter. You have current flowing from collector to emitter, right? IC or IE. Let's just stick with IC, okay? So IC is flowing from collector to emitter. And then depending on the external voltage that you're applying, that current IC would be fixed. If you apply 5 volts, you will have a certain, let's say you get 5 milliamps, depending on circuit configuration. If you apply 10 volts, you might get 10 milliamps. But regardless of what the voltage source is, once you connect a voltage source, that current will be fixed. There's no way that you can change. So there's a third terminal that comes into the picture. And the third terminal is the base. So current is flowing from the top to bottom, collector to emitter, and then you insert a third terminal in there. And the third terminal allows you to control the flow of current that's coming from the collector to the emitter. So IB controls IC. Okay. IC changes as a function of IB. And the relationship, obviously, from this equation we can write is IC is beta times IB. This is one of the most important relationships, right? Beta is the ratio of IC over IB. And I believe I showed an example where you have a small AC signal and you apply it to a large DC component or large DC value, and the shape of the DC output changes. Right? For an amplifier to work, your IB would be a small AC signal, and you're applying a large DC voltage on the output side. So this is your large DC voltage. And the resulting output would be this. Okay, a small change at the base terminal results in a large signal at the output. And that's why we can use the transistor as an amplifier, because the collector output follows the input at the base. All right, let's take a pause. Let me know if you have any questions. Anyone? Okay. All right. Oftentimes in the problems, we are given beta, we're not given alpha. But here are quick handy equations that we can use to determine the relationship between the two. If you're given beta, we can find using alpha over 1 minus alpha. And if you're given alpha, we can find beta. Okay. So that's the BJT terminal currents and voltages. The output characteristics are on both sides. Okay. So it's a 3-terminal device. We have an input side and we have the output side. Typically, the base and the emitter regions would comprise the input, and the collector and emitter regions would comprise the output. So there is input characteristics and output characteristic. Input characteristic is typically simply a forward bias PN junction diode. So it looks like this. That would be IB, and this would be VBE. okay, IB and VBE. So if you apply an AC signal, it simply looks as if you're applying a sine wave to a forward bias PN junction. Okay. On the output side, it's quite different. Output characteristic is the collector current as a function of VCE, a function of voltage. So VI characteristic or IV characteristic is typically voltage on the x-axis and current on the y-axis. So let's say you have a particular input applied at the base. Okay. Particular input applied at the base. And that input was like 10 microamps. So 10 microamps input at the base, and you try to measure the collector current. Let's see. It will be somewhere here. It is so small that it may as well not be flowing through the device. Okay. And I'll explain what that means. Okay. Depending on the transistor, depending on the circuit, you may not have any current flowing at the output. Okay. Then you slowly increase the input voltage, the input current on the base side. Let's say you apply IB as 25 microamps. So for an input of 25 microamps, if you plot the value of, and I'm going to zoom into this, the collector current is going to rise, well, I'm going to say linearly for just a little bit. Again, there are many complexities involved, but let's just say it's rising linearly. So collector current will rise linearly with increasing collector emitter voltage, VCE. After a certain point, it will quickly saturate to a level. And from that point on, the collector current remains constant. And you get a flat line, no matter how much you increase the VCE. Okay. So again, for a single particular input, you have one curve representing IC as a function of VCE. As VCE increases, IC starts increasing for a very short period of time. That relationship is linear, after which it will quickly reach a saturation level. And after that, so this would be saturation. And after that point, the output current will remain constant regardless of what the value of VCE is. Does everybody understand that? So again, when IB, the input is so small, the output is not available. We refer to that as cutoff. We say that the output is cut off. And when you obtain output for any particular value IB, it quickly saturates, and then we obtain a flat output profile of the collector current. Now, the point at which it reaches saturation is individual and depending on the biasing circuit. It depends on the biasing circuit. And of course, the transistor itself. Now, if we change the input, let's say we go to a higher level. Okay. This was, let's say, I will stick with the graph. Let's say this was 25 microamps. And IB is now 50 microamps. Now, IC can go to a slightly higher level. So IC increases as a function of VCE, but once again, it will saturate. And from that point on, the output current is near constant. And so we keep doing this for different values of IB, and we obtain a set of curves or a set of data points for the collector current as a function of VCE. And each one of these curves that you see here could have like 15, 20, 100 data points. Doesn't really matter. But again, transistors remain and behave like a constant current source because the output current is constant. Okay. All right, let's take a pause. Think over that. Let me know if you have any questions. Yes.
I can kind of confuse that. That's the part where they're both very flat. Is the saturation like saturated?
Yeah. So the question being asked is, why is this not considered the saturation region? It's a very valid question. I had the same question when I was a student, and I still have the same question about the nomenclature. But the point being that we want to treat each of these regions differently. So the bottom, we say we have the cutoff region, which is, that's quite straightforward, I would think, right? Because there's no output coming, and so we just say it's cut off. We could say that all of this is the exact same region. But when we, depending on our application, if you want to use it as a amplifier, we need to separate out these into two distinct regions. And that's why we call this as the saturation region. This is the region where the current starts or begins to saturate. Okay, that's when it starts to saturate. And this occurs for voltage VCE values of less than like 0.2 volts, typically 0.2 to 0.3 volts. Saturation, VCE is equal to 0.2 volts less. Okay, so this is the region where the current begins to saturate. Hence, it's known as the saturation region. Now, if the transistor behavior was exactly the same in the rest of the region, you would pretty much say it's the saturation region all over. But this region is used for amplification, and it's known as the active region. It's known as the active region. There is also another reason why those regions are different. It has to do with the biasing of the two PN junctions. Okay. So let's look at that. Operating modes. So we have three distinct regions. We have cutoff, we have saturation, and we have active. If we bias the transistor to operate either in cutoff or in saturation, we can use it as a digital switch. So we can use it for digital logic applications. If we operate the transistor in the active mode, we can use it as an amplifier. And so those are the applications we saw in labs 3 and 4. Okay. If you operate the transistor in cutoff, then we say transistor is, or the switch is off. In saturation, the switch is on. The switch is on. See, one other important thing to answer that question, the other question is, in saturation region, once the transistor is in saturation, we can't change the output. The output current remains constant. Okay, output current remains constant. When it's in the active region and you're still changing the input, the output will change according to the input. When it's in the saturation region, it will not change. It will just go to a maximum level, and that's the level you'd obtain. As an example, when you did lab 3 and you did lab 4, the final waveform that you'll obtain, did anyone obtain like a clipped waveform or a non-sinusoidal waveform? So if you obtain, so if this is your sinusoidal waveform, someone might have obtained something like this, and this would be cut off, might have obtained something like this would have been cut off. And so the only waveform you saw was probably something like this, like a square wave or some sort of oddly shaped waveform. Do you remember from lab 3 and 4? The reason that's happening is because it's driving, the input signal is so large and the gain of the amplifier is so large that even though we want to operate the transistor in the active region, the input sinusoidal waveform is driving the transistor into saturation and cutoff. And so it's clipping the top and the bottom portions of the waveform. Okay, that's what's happening. So if you have distortion in the output, it's a result of driving the transistor into saturation and cutoff. That's why biasing is very important. Biasing is the application of DC voltages and determining the resistances for the amplifier circuit, or the transistor circuit. All right. Any other questions? Okay. All right. So operating modes. This is how the three operating modes typically function. We are showing this for an NPN transistor. It's an NPN transistor. So if both junctions of that NPN transistor, meaning this is the first PN junction, collector and base, and this is the second one, which is the base emitter. If both PN junctions are reverse bias, then the transistor is in. What operating mode do you think the transistor is in? There's only two choices: cutoff, saturation, or active. It's in cutoff mode. So both junctions are reverse bias. The emitter base junction is where the charge carriers originate. So if that first junction itself is reverse bias, then the transistor for sure is in cutoff. That's why your transistors would not work in a circuit if you reverse or flip the terminals. Because if you forward bias the collector base junction, the collector does not have enough free charge carriers, the transistor would not function. It's not a symmetrical device. Right? That's why terminals or pinouts are very important. Does that make sense? If you reverse bias both PN junctions, the depletion region increases, and base region keeps on widening actually. And then transistor is said to be cut off. If both PN junctions are forward bias, meaning the base voltage is larger than both the collector and the emitter voltages, both junctions would be forward bias. When both junctions are forward bias, the transistor is said to be in saturation. Okay, so the transistor is in saturation. That's in a saturation region. So cutoff and saturation is when the transistor, the base signal going into the transistor would either drive the transistor into saturation or cutoff. So if it goes into cutoff or saturation, those modes combined, we can use it for digital circuits because we can use it for switching. Binary number system, zeros and ones. If the transistor is cut off, it is off. Electrically speaking, it's an off switch. We can represent it in binary mathematical terms as logic 0. The transistor is in saturation, It's on, current's flowing through. We say it's an electrical switch, it's on. We can represent in a binary number system as logic 1. This is the foundation of all digital logic circuits. And then we come to one of the most important applications as an amplifier. Requires the emitter base junction to be forward bias. So this is N, P, and N. The base is forward bias with respect to the emitter. So it's a forward bias PN junction. The voltage between the base and the emitter, VBE, will always be 0.6 volts or 0.7 volts, depending on the text that you're using, depending on the transistor that you're using. So this would be 0.6 volts right here. And then collector base junction is, of course, reverse bias. Right? Collector base junction is reverse bias. And this mode is known as the active mode of operation. This active mode is also referred to as the forward active mode. Okay, forward active mode. In general, we simply refer to it as the active. Again, the emitter is the most heavily doped material in the transistor. And so that is where the charge carriers are originating. If you flip the terminals, let's say you're building a circuit, you configured it incorrectly. Now your collector is where the emitter should be. So if you have an NPN transistor and you have the collector, you have the base, and you have the emitter, instead of forward biasing the base, let's say you forward bias the collector and the base junction. So instead of forward biasing the base and emitter junction, you forward bias the collector base junction. What do you think would happen? It's a PN junction, you're forward biasing the PN junction. What should happen? We would expect current to flow, right? But current only flows if you have charge carriers. It's basically like taking an intrinsic piece of silicon and applying voltage to it and expecting current to flow. It's not going to work because there are no free charge carriers present. And so if it's very lightly doped, like the collector is, even though we forward bias it, pretty much no current flows through. Almost no current. And then, of course, we reverse bias this, and absolutely no current except for IS. And this mode is known as the reverse active mode. This is not something that we use for anything, even in E classes. We simply bring this up so that students can understand that if your transistor is not working, it may perhaps be in reverse active mode. Reverse active mode would be for all intents and purposes, reverse active mode would be the same as cutoff, except that it has no purpose whatsoever. If our circuit is not working, that is a check that we can perform on our circuit. Okay, there's no purpose to this. And no application, at least none that I know of. Okay, it's just something that we should be aware of. Right? So now you would ask the question, but if we bias the transistor to be in active mode, we want to use it as an amplifier, then how can it go into cutoff and saturation? Right? How can we? Biasing comes from the external applied DC voltages, both on the input and the output side. So if the externally applied voltages are not changing, how does the mode of operation change? And the answer to that question is the mode of operation can change because of the applied AC signal at the base. When you apply an AC signal at the base, you have every single point in time, you have a flat constant DC value. And on top of that DC value, you're now applying an AC signal. So it's either adding or subtracting from your input going into the base. And because that happens, that shifts your operating point. And your operating point shifts, either your transistor is going in cutoff or saturation if the circuit is not very well designed. And that's how a transistor biased in the active region can be driven into saturation and cutoff. Let's take a pause, think over that, and let me know if you have any questions. Let's see what else. Configuration. Get through at least 2 more slides. Questions? Okay. All right. You're going to use the common emitter configuration. I'm just going to quickly show the input and output characteristics. So we have a biasing, and we typically refer to this as VCC, collector side biasing voltage. And this is referred to as VBB, the base side biasing voltage. If you apply a biasing voltage to the emitter terminal, meaning if you have a common collector or common base mode, we would have VEE. So emitter biasing, the supply would be referred to as VEE. Okay, this is to differentiate between the voltages of the terminal voltages of the transistor and the applied external voltages. Right, so we have VC, which is the voltage at the collector. Then we have VE, and we have VB. So the externally applied voltages, we refer to them as VBB and VCC. So these are the input characteristic curves, and these are the output characteristic curves. Input side, we simply have a forward bias PN junction. So it's a diode characteristic curve. On the output side, again, we saw those output characteristics just a few slides ago. And then the same thing for a PNP transistor, except the polarities of the voltage sources are flipped, holes and electrons are switched. And so current direction is opposite, voltage polarity is also opposite. Okay. Everything else remains the same, but because they're in the opposite direction, it's now being plotted in the second quadrant. So voltage VBE is actually VEB. Okay, VEB would be positive, but standardized plots, you always refer to as IB as a function of VBE. So VBE is negative. PNP transistor. Nothing else changed. Functionality and everything else remains the same. And same thing happens on the output side. Okay, VCE would be measured as negative. That's the only thing. So determining operating mode. Okay. You know what? Let's just end class here for today, and then next week we'll pick up with the example of operating mode, and then the other applications. All right, quiz as usual on Monday, based on the material we have covered this week. No BJTs, but Zener diodes. So Zener diode and voltage regulators. Okay. All right, have a good weekend, and I will see you all on Monday.